Hi, it's Wendy Olsen. I'm at University of Manchester covering beginner Bayesian reasoning. It's about 1 hour of lecture. You can break off and return to it. I'm going to show you what it will consist of and how you can break up your time. I'll also be showing you how to do your studying on this topic of Bayesian. And it's meant for anyone. It's open to all. It could be in social sciences, could be a researcher or a professional. What's this Bayesian reasoning and how to apply it and how to get going on these models. So I've got my computer there. You can get the slides from Dropbox by the link that's underneath this video. And I'm really happy to be able to introduce you to Bayesian. I'll just tell you what the lecture consists of so that you can decide how long to stay with me. I've got the basic concepts first of all for about 20 minutes, probability and probability distributions, and running right into likelihoods and the posterior, which is an important part of Bayesian. Then binomial models, that's discrete models for outcomes. And lastly, continuous variable models. So I'll be explaining how you can combine data and how you can even have qualitative data or Facebook and other online data entering into your model. It's not a purely statistical thing. It's about social research, about the society. So this introduction is followed by intermediate and advanced work. We have programming work. We have lots of students. The room's full. And we've been able to share this with a number of people from various disciplines, like sociology and economics. And I'd like to thank some authors first before I start. One is Eric Wisniewski. He's a brilliant demographer and social statistician. And the red marks in our slide are about our social statistics degree programs that he helps me to teach. And also Bayes. So the date of Bayes' theorem is about 1763. And the authorship of it is contested. As usual, there were more than one scientist reaching this conclusion. But this was really at the beginning of the Enlightenment science debates. And you can see on the slide the way that the Bayes theorem might be presented. It depends heavily on the concept of conditional probability. So I'm going to explain conditional probability briefly. Just reading out, the probability of A given B is a ratio. So it depends on two other things, and one of them is the probability of B, because clearly B has to happen for the A to happen in the sense that we're looking at A given B. So this vertical dividing line means given, or conditional on. And so on the right-hand side, the numerator is the probability of A and B, it's the intersection. And so we'd have the ratio of that to the probability of B itself would give you the probability of A given B. So the thing in the numerator is the joint probability. And it is transitive between A and B, but the thing on the left is not transitive. And so what Bayes came up with was by reversing the roles of data and model, or the roles of the unknown and the knowns, he was able to start making statements about what could be known that were different from anything that had come before. So I'm going to try and explain that. And we'll keep returning to this slide and this formula as we go through the talk. So we have Bayes' theorem again, but now we have theta for the parameters, and we have a d for the data. So it could be a matrix of data. And we say the probability, but here it's not a single number probability. Now it's a distribution. It's really clear now that it's not just a series of incidents. And it depends on, equals, the probability of the data given that model times the probability of theta. Now these are very strange concepts here. The one on the right is called the prior. It's the prior probability of theta. Or in other words, what do we know about theta already? So I'm going to use an example from Cowles's book, Mary Catherine Cowles, Applied Bayesian Statistics. It's a really nice book, and I do like it. And she uses the classic cancer example, where the treatment is before we get to the treatment, we have to decide whether they really have cancer, and they usually do a test. So they have a test like mammogram, or doing perhaps a slide based on an extracted biopsy, and they actually know the population prevalence of cancer while they're doing those tests. So P of theta turns out to be the probability of cancer in these particular discrete tests, whereas the probability of the result, given that background probability, might be an unknown. But then we get the data, and then we have the probability of D, which is a bit strange, right? If you have the data and there's one datum, one test, then shouldn't that just be a 1? But it turns out there may be several alternative options for the outcome. There might be 4. So test yes or no, and cancer yes or no. So you'd have no, yes, no, no, yes, 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 no. 4 options. So the sum of those would be P of D in the denominator. And overall, it's quite a complex theorem, so we'll keep looking at parts of it. Here I convert the ratio into a proportion in the second row. So the proportion is allowable because of that 1 possibly being a 4 or a 2 or some other sum. Actually, the denominator could be any integral, and it would integrate out to a constant. So it's just a constant term. It's not that important. The interesting things have to do with the parameters that are in theta. So theta might be a whole bunch, like a vector or a set. Could express it with brackets, alpha, beta, gamma, all the unknown terms. And they themselves might be vectors. So theta could be a whole matrix of unknowns. And it's proportional to the likelihood on the left times the prior. And this term likelihood might not be familiar, so I'm going to try and explain it and unpack it a bit. But can I just remind you, looking at that previous slide, about whether these are numbers or distributions. So for a single number, you might have a single event, A, or a single event, B. But you could have that A is all the scores of all the children in a class, and B is all the incomes of all their families. So it'd be a background factor. And in that sense, this can all be notation for much larger conditions than what we had originally spoken about. And then in the end, on the left-hand side, we're going to have the posterior probability. So the multiplicative product of the likelihood and the prior is going to be the posterior. What's that? It's afterward. So if you knew the prior probability of cancer, and you got the cancer test, they go on the right. Or even a bunch of cancer tests. And then we could work out the posterior probability for this particular sample of the risk of their having cancer. And it might be higher than the average, or the prior. Can you see how prior information can go into that prior, even if it's not very good information, and then we'll update it using the data, which is new, and then we'll be able to get this posterior, which is afterward, after looking at all the data. So that's how the theorem works, and it's a great thing. It's really powerful. So here I've written it again with theta, and I've said that the posterior is proportional to the likelihood and the prior, to the product of those two. So it's just really getting used to this way of expressing things. I like to think about reality rather than variables. So I like to think the data depends on reality, and it's giving us a glimpse of reality. So, of course, reality is not fixed. It's not just material. It's very complex. But theta depends on that reality, and so that corresponds to, in my third line, it corresponds to the probability of the theta estimate, theta hat. So this caret means making an estimate of all the parameters given D. So D is the information. Now you can put into D the information from publications that give you information about cancer, or you can create a meta-analysis by putting all the other analyses into D, and then maybe updating that with some new information, or even just combining them to get the posterior overall probability, merging all those samples. It's really interesting what you can do with this. So I will be talking about applications in a moment. So this likelihood, though, it's not just a scalar number, it's a function. So it's a function of theta here, or it might be a function of the data. And the data could change. So you could set up your Bayesian model, declare everything, and then you might go and get some more data, issue some more questionnaires, or scrape it from the internet, and then put those in, and the results would change afterward. So that's posterior probability. So we're getting the idea that the likelihood is something in the middle of this work, and the posterior is at the end of the work afterward. How do we derive that? Well, it turns out it's quite easy to derive a likelihood, and it's used in a lot of other statistics. So the beginner usually learns ordinary least squares estimation with the minimizing of the distances from a line to the points. But the intermediate student learns maximum likelihood, and that refers to the same likelihood, the one that I'm depicting on the screen here, the probability of the data given the model. But they learn it for a single model, whereas in Bayesian we can have several models. So I'm going to run through some more of these concepts. So for the likelihood for a single individual case or a treatment or a trial,